Probability, a random experiment. The outcomes totally depend on chance. The outcome can't be predicted, so that's a random experiment. Rolling a die. You have 6 sides, you roll it, it's a fair die, you don't know which side's going to come up, so that's a random experiment. Or pulling a name from a hat. You've got a hat, and you've got everyone's names written, once on each piece of paper, you pull out a name, you read it. The sample space is the set of all outcomes. So if you're rolling a die, it would be like you can get a 1, 2, 3, 4, 5, or 6, and we call that omega, which is the last letter in the Greek alphabet. Let's say you had this spinner, like a number spinner. Let's say you have a spinner like this, and every time you click on the arrow, it spins, and it picks a number. And if I press reset, each time I spin, I can pick a different number. So this is totally random. I can get like 9 twice in a row, or 3 times in a row. Not going to be very likely, but these are the different outcomes that I can get. The spinner, it would have an omega of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are all the different outcomes you can get. So an event would be some subset of the sample space. Clara wins in the event C when a prime number is spun. Clara would win if 2, 3, 5, 7, or 11 comes up. Morgan wins in the event M, an odd number is spun. So M is equal to 1, 3, 5, 7, 9, 11. So the probability of an event is equal to the sum of the probabilities of the outcomes that make up that event. So the probability of Clara winning is equal to the probability of a 2 being spun, added to the probability of a 3 being spun, added to the probability of a 5, added to the probability of 7, added to the probability of 11. Probability, it's the number of desired outcomes out of the total number of outcomes. How many desired outcomes do you have? 1. Out of how many? 12. So the probability of 2 coming up is 1 out of 12. The probability of a 3 coming up is 1 out of 12. The probability of 5 is 1 out of 12. The probability of 7 is 1 out of 12. And the probability of 11 is 1 out of 12. The probability of Clara winning is add all these together, but it's 5 out of 12. A simple event has exactly one outcome. So let's say Belinda wins in the event of a 7 being spun. That's called a simple event. Compatible events. These are also called non-mutually exclusive events. Events that can happen at the same time. Can Clara and Morgan both win at the same time? Remember, Clara is the prime numbers and Morgan are the odd numbers. Can we spin a prime number and an odd number at the same time? Sure. If a 3 comes up, they both win. Or if 5 comes up, they both win. Or if 7 comes up, they both win. Or 11 comes up, they both win. These are compatible or non-mutually exclusive. Clara and Morgan can both win if 3, 5, 7, or 11 comes up. And notice C intersection M is not equal to the null set. If we look at what is common between these two things, they have something in common. If they had nothing in common, then they would be mutually exclusive, or they would be incompatible. Incompatible events, or mutually exclusive events. These events can't happen at the same time. Let's say Rachel wins in the event R, that an even number less than 10 is spun. That's 2, 4, 6, 8. And remember, Morgan wins if an odd number comes up, so 1, 3, 5, 7, 9, or 11. Can they both win at the same time? No. Whenever Rachel wins, Morgan loses. Whenever Morgan wins, Rachel loses. Rachel and Morgan can't both win at the same time. Notice that R intersection M is the empty set. Like there's nothing in common between 2, 4, 6, 8 and 1, 3, 5, 7, 9, 11. Complementary events are incompatible or mutually exclusive events that together make up the sample space. Let's say Zena wins in the event Z of an even number being spun, 2, 4, 6, 8, 10, 12. Morgan wins if an odd number comes up, 1, 3, 5, 7, 9, 11. Whenever Zena wins, Morgan loses. Whenever Morgan wins, Zena loses. They both can't win at the same time, and they both can't lose at the same time. If Zena loses, then Morgan must win. Together, they make up the whole sample space. Zena, union, Morgan, all together, take them all together, you have the whole sample space. The probability of Zena winning added to the probability of Morgan winning has to be equal to 1. Let's say the probability of Zena winning is 6 out of 12. The probability of Morgan winning is 6 out of 12. Add them together, you've got 12 out of 12, which is 1. We can also think of this in terms of A and not A. Right? So if you have an event A rolling a number less than 4, so 1, 2, 3. Not A would be rolling a number 4 or greater, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the probability of A would be 3 out of 12. The probability of not A would be 9 out of 12. Add them together, you get 1. This is called A prime, or A with an apostrophe, but we call that A prime, is called the complement of A, or not A. The probability of an event. Let's look at an example. A drawer contains 8 knives, 10 forks, and 12 spoons. 2 simple events are considered: taking out a knife and taking out a fork. So you and your sister are playing a game where you reach into the drawer with your eyes closed and you randomly pull out a single piece of cutlery. You win if you pull out a knife or a fork, but she wins if you pull out a spoon. What's the probability of you winning? The probability of getting a knife or a fork would be the probability of getting the knife added to the probability of getting the fork, which is 8 out of 30. Because remember, we have 8 plus 10 plus 12. 8 and 12 is 20 plus 10, 30. You have 30 pieces of cutlery, and you have 8 knives. So the probability of getting a knife is 8 out of the number of cutlery pieces, 30. The probability of getting a fork, you have 10 forks out of 30 cutlery pieces. We add them together, that's going to give us 18 out of 30, which we can reduce to 3 out of 5. We could also write that as a decimal, which is 0.6. And we can also, is writing it as a percent. 0.6 is 60%, so there's a 60% probability of you winning. Random experiments with several steps. So the probability of an event is equal to the product of the probabilities of each sub-event. For example, if your 2 marbles are drawn from a bag containing 10 marbles that are the same size and numbered 1 to 10, the probability of the event draw marble 3 followed by marble 7 would be written as, this is with replacement, so you're pulling out the 3 and then you're going to put it back. So we're going to look at 2 examples. We're going to look at with replacement and without replacement. So you pull out a marble, you look at the number, you put it back. So that's with replacement. So the probability of getting 3 and 7, it's going to be equal to the probability of getting a 3 multiplied by the probability of getting a 7. The probability of getting a 3 is 1 out of 10. You put it back, so there's still 10 marbles in the bag. So the probability of getting a 7 is 1 out of 10. So that's going to give you 1 out of 100. But without replacement, these 2 events, getting a 3 and getting a 7, are said to be independent because the probability of getting the 7 doesn't depend on the probability of getting a 3. But if we don't replace them, it changes. It becomes a dependent experiment. The probability of getting a 3 and a 7 would be equal to the probability of getting a 3 on the first draw multiplied by the probability of getting a 7 on the second draw. The probability of getting a 3 on the first draw is 1 out of 1 marble, the 3, out of 10 marbles. But now you're not replacing the marbles, so you only have 9 marbles in the bag. So the probability of getting a 7 is 1, the 1 marble, the 7, out of the 9 marbles that are in the bag, which gives you a 1 out of 90. So let's look at union and intersection. We talked about them a little bit before. A union B. Union, we could also think of it as or, like A or B. If A is on the spinner, spinning an even number, and B is spinning a prime number. So you would win if A or B comes up. If you spun an even number or a prime number, you win. A would be 2, 4, 6, 8, 10, 12. B would be 2, 3, 5, 7, 11. You win if A or B happens. If A is 2, 4, 6, 8, 10, 12, and B would be, we already have the 2 there, 3, 5, 7, and 11. You win if either comes up. So it's just basically this whole space here, like that. So A union B would be take them all together. Think of union, to unite them, to put them all together. A union is when people all get together on something. You win if 2 or 3 or 4 or 5 or 6 or 7 or 8 or 10, 11 or 12 comes up. Union is all together, and we can think of it as or. You win if A or B comes up. Or you can think of it as you get to keep what's in A or in B. Intersection. A intersection B. We could also think of the intersection as and. Same example, spinning A is spinning an even number, B is spinning a prime number. We're thinking you win if A and B both happen. A is 2, 4, 6, 8, 10, 12, and B is 2, 3, 5, 7, 11. You win if A and B both happen. So you can only win if the 2 comes up. If we look at the Venn diagram here, you have the A, I've shaded it this weird pinkish red color, and B is this yellow color. And notice the intersection, where they overlap, is orange.
This circle represents people who are breaking my heart. And this circle represents people who are shaking my confidence daily. And where they overlap, Cecilia.
So you win only if the 2 comes up. A intersection, what's in both A and B? 2.
This is Joni Mitchell. This is her thumb. And this is all about the rule of thumb. And if you have the word and in a probability question, if you're flipping a coin twice and you win if you get heads and tails, so heads on the first flip and tails on the second flip, you're going to end up multiplying. But if you have the word or, let's say you're flipping a coin twice, you win if you get heads tails or tails heads. We're going to add. some probabilities. I'm going to show you those two examples. Example 1, you win if you get heads and tails on 2 flips of a coin. So if we start, first flip we can get heads or we can get tails. We start with a whole chance. Half the chance is going to go this way, half the chance is going to go that way. Then we're going to take that half a chance is going to be split in half. So half of the half is going to go this way, half of the half is going to go that way. Now if we flipped and we have heads, the probability of getting heads is 1/2. The probability of getting tails is 1/2. But we're saying the probability of getting heads, provided you got heads on the first one, is 1/4. Let's see why that is. So we start with a whole chance. We're cutting that chance in half and in half. On the second flip, you have a half chance of getting heads, you have a half chance of getting tails, you have a half chance of getting heads, half chance of getting tails. But what we're saying is if you start off with a whole chance, half goes this way, and then half of the half goes this way, which is 1/4. The probability of getting heads, 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 tails, tails, heads, or tails, tails is going to be half of the half, which is 1/4. Half of the half again, which is 1/4, which is 1/4, which is 1/4. You win if you get heads and tails is a half of the half. So we're multiplying down the branches. If you have more than one step inside your outcomes, then you end up multiplying as you go down the branches. If you have more than one branch, we have 2 steps. We have a first flip and a second flip, but we end up multiplying down the branches. So we're looking for heads, tails, and the probability is going to be, probability of heads and tails is the same as the probability of getting heads on the first flip times the probability of getting tails on the second flip, which is 0.5 times 0.5, which is 0.25. Multiply along the branches. So as you're going along the branches, you multiply, which is a good rule of thumb. And we multiply or we add. Example 2, you win if you get heads and tails, or if you get tails heads on 2 flips of a coin. We start, we get the first flip, we can get heads or tails. On the second flip, we can get heads or tails. We have a half chance of getting heads and tails on the first flip. On the second flip, we have a half chance of getting heads and tails. So our probability doesn't change on the second flip. The probability of getting heads, heads, it's going to be a half of the half, which is 1/4, like 1 out of 4. We have 4 equally likely outcomes, and this is just 1 out of 4. But we got them by multiplying down the branches. We win if heads, tails comes up, or tails, heads comes up. So we win if this comes up, or if this comes up. Whenever that happens, we're going to add. We're looking at the probability of heads, tails added to the probability of tails, heads, which is 0.25 plus 0.25, which is 0.5. So we multiply along the branches, but we add down the leaves. Like think of the endpoints as being the leaves of the tree. And that's our rule of thumb.
Independent events. One event happening does not change the probability of the other. If you are rolling a 5 on a die is, let's say, event A, and event B is rolling a 4 on a die. If you're rolling the die twice, what's the probability of getting a 5 and then getting a 4? That would be the probability of getting 5 and 4. So the probability of rolling the 5 and rolling the 4 next would be the probability of rolling the 5 times the probability of rolling the 4, which would be 1/6 times 1/6, which is 1 out of 36. So these are totally independent. Notice the probability of the second one isn't affected by the probability of the first. What's the probability of rolling a 5 times in a row? Well, it's no different than rolling 5, 3, 2, 6, 2. Rolling 5, 5, 5, 5, 5 is the same as rolling 5, 3, 6, 5, 2. They're equally unlikely. Dependent events. So one event happening changes the probability of the other. For example, let's say you take, out of our class, you take 10 names and you put them in a hat. You're choosing 2 people, one to be president of the class and one to be vice president. A is choosing Mahiba and B is choosing Angie. A is choosing Mahiba on the first draw and B is choosing Angie on the second draw. The probability of getting Mahiba Angie would be the probability of choosing Mahiba times the probability of choosing Angie. Because we're pulling them out of a hat and we're not putting them back, the probability of choosing Mahiba, well, Mahiba is 1 name out of 10 names in the hat. Then, because you're not putting Mahiba's name back in, she can't be president and vice president, now there's only 9 names in the hat. The probability of choosing Angie is 1 out of 9. This circumstance would be dependent events, whereas up here, that would be independent. And we could make the experiment with picking a president and a vice president from a hat, we could make that independent by putting the name back in. So we pull Mahiba's name out, we look at it, we put it back in, and there's still a 1 in 10 chance of getting Mahiba or Angie. You still have 10 names in the hat. So that would be independent. And that is it for Introduction to Probability. Have a good day.